couple of things I wanted to point out. 3 people didn't do the last 2 problems. I'm not sure why, but it seemed odd that all 3 of them did the last 2, so I don't know what's going on there. The second issue that was odd as well, we were calculating G0 through G5, and several people, including my solution, which I don't really understand, had a reward for R1 of 1 instead of -1. And so I don't know whether somehow we're looking at different PDFs, that possibly a draft that had a different number there, but you have
I think when you I don't know, but I mean, for me, when I copy and paste from PDF to Word,
that's what happened, because that's what I did.
Written in negative.
So we lost the negative and the copy for the PDF. Okay. On all these things, you know, I still give full points. I just mark it as correct or incorrect. And I don't remember on the negative whether I marked it as correct or incorrect, but it doesn't really matter. I'm just so that explains my way. Yes.
How do you actually go about calculating G5 if you only have R5?
G5 is 0.
Okay.
Yeah, it's defined at the end, it's just be 0. And then you work through that. There was a little confusion, a couple people were sort of off by 1 in the senses of, you know, remember that GK equals RK plus 1. As far as the constant, adding a constant, right? When we talk about the continuing tasks and adding a constant, if we look at G sub K, let's say, so that equals R sub K plus these other values. And then we can just define, let's say, GK prime equals RK plus some constant plus, and add a constant everywhere. And that's great. And a lot of people then went through and showed the relationship sort of between GK prime and GK as GK plus C over 1 minus gamma. And that's great, but that's not actually what the question was. So the question was not show that these were rewards, but it's instead show that the value functions are the same as the old one plus a constant. So in order to do that, you actually would need to say something like, you know, V prime of S equals the expected value of GT where ST equals S. Right? And then we can say, okay, let's define our V primes to be these G primes. And then we can say that's the expected value of GT plus C over 1 minus gamma, given ST equals S. And then we can pull this out of the expectation because it's just a constant. Should be using consistent lowercase here. And then that is just equal C minus 1 minus gamma plus. So we have this relationship between V prime and V. Okay. So you should go that full step. Many people didn't, and actually originally my solution didn't either. But I realized I should, as I looked at some good examples. On the comments, I sometimes say to see the solutions. As I'm remembering, I don't think I've actually posted the solutions yet, so I will do that in the cafe when I come here. The last one that actually there were a lot, many people got right. Many people hand-wavy got right, or intuitively got it right, and then many people got wrong too. And that is taking this to the episodic case. Right? So this is the continuing case. And if we take it to the episodic case, and say, okay, if we just add a constant, does it make a difference? Right? It doesn't matter in the continuing case, because of the fact that all the values, we've just shifted all of the values by the same constant, right? So taking the match and things doesn't really matter. We just move them all. And relatively, they're the same. And the question is, in the episodic case, is that the case? There are a few intuitions that you can use here. One intuition is, in the episodic case, the length of the episode is going to have an effect on what the value of the state is going to be, right? If you have a 2-length episode, that's going to add 2 of the constants. Whereas if you have a 4-length episode, that'll add 4. Ignoring for a second the discounting. But longer episodes will add more of the constants, shorter episodes will add less of the constant. So it seems like that's going to have an effect. And I think the best example to show why it does make a difference is the maze. And if you came up with, or so you have a maze and you want to get out as quickly as possible. And so we decided for the episodic case, one way to do that would be have -1 reward in the maze and 0 at the exit. Right? And so clearly, by maximizing the reward, you're going to minimize the time you spend in the maze. Now, let's just add a constant, like let's say 2 plus this and 2 plus this. And now all of a sudden, our incentives have changed completely. Right? Our goal is stay in the maze as long as possible. Right? As someone said, aimlessly wander in the maze. And from my point of view, it's not aimless. Aiming at not doing the exit. Right? And so then you can get an unlimited amount of reward. So that's the best example. And get through to the hand waviness. If you give a specific example, then just show how all of a sudden the optimal policy is going to be quite different. Any questions on this?
So just to clarify, continuing just means everything is, so one confusion for me is like when I was thinking of episodic is like set like discrete time steps, but continuing still has those time steps, it just lets those time steps go to infinity.
Yeah, you just have something that is never going to end. So, and the episodic says there's some end state of this.
And then in the like larger scheme of all the reinforcement learning problems that we consider, do we ever have a case where we don't make that approximation that we need to have like, you know, something is happening at this time t and then t prime and so on and so forth? Like, if we have, you know, I feel like our sense of time is like things are just happening. And I guess we can discretize it however we want, but is there ever a reinforcement learning that just allows for, that's not so rooted in time?
No, although you don't have to think of time as equal time intervals between these time steps.
Okay.
So it could certainly just be when an action happens.
Right.
Right, that's a time step. And then there may be nothing that happens, and then there's another action, and that's a time step. Or it could be we have a beat every second is a time step, and the doing nothing is an action of choosing not to do anything. That would be the case in an arcade game, for example. No questions? So let's just review a moment. We've gone over on Monday. So we have policy evaluation. Policy evaluation. Let's see. Daniel, give me a short description of what policy evaluation is. If I could do 3 symbols, what would they be? And I'll give you the second one.
I
Where do you want it?
to the
Okay.
left, and then the evaluation of the policy I.
Okay, and what symbol might we use for the value of the policy line?
V. of pi.
So high, sure. Okay, so that's policy evaluation, right? And then policy improvement. Julius. On do you want pi on the left or the right?
Left.
Okay.
And then you want to get I prime.
Okay. So, oh, sorry, you said prime? There's prime. Okay, so that kind of makes sense from its description. You improve a policy, you take a policy in, and you get a better policy out. Not actually the case, though. If we look at our general policy iteration, our policy iteration says we take a policy pi sub 0, and we come up with v pi sub 0, right? And then we construct a policy based on this v. We don't care about our pre-existing policy. So we just say greedily, create a policy based on a value function. So therefore, what's on the left-hand side here? If it's not a policy. It's not the state, it's actually a value function. So we take just a value function that was with respect to some pi. So it's the fact that it was with respect to some pi that kind of gives us our improvement. So the value function with respect to this pi gives us an improved policy. Does that make sense? The distinction makes sense? We don't actually need the policy here because we got everything we needed from the policy when we created or calculated the value function. And now we just take that value function and create a new policy. And then we just feed this back into this nice shape. And what we know also, at the end of this, what's the relationship between pi and pi prime? Sean. So after we do one of these steps.
Relationship between pi and pi prime.
Yeah, the policies. Which one's better?
Pi prime must be at least as good.
I like that. At least as good. What if it's, so it could be equal?
Yes.
And if so, what does that mean?
That means we converge to the optimal policy.
Exactly. So if this guy, if we didn't get any improvement, there's nowhere to improve to because we've converged to the optimal policy. Otherwise, we got an improvement. Okay, so if there's a difference, it's an improvement. And if we don't have a difference, we're done. Clear? Now,
Is it possible to go pi prime to like converge to like one instead of like this?
no. It can't converge to a local minimum.
In the reading for today, it mentioned that in certain episodic non-discounted tasks, if you're using dynamic ordering to update, not necessarily sequentially, but when
If you're
to,
moving around, yes,
right,
but there it
there are
is.
cases where it doesn't converge. What would that look like? I might be getting ahead of.
No, it's a good question, which I will put on my list to figure out. Because I don't have the answer right now. So, in the case where we're going through and evaluating all of the states and converging on that policy, and so converging on the value function, then we'll be fine. We're going to talk about these asynchronous updates in a moment. And I'll come back to you on Monday as to how the peculiar situations in which they can fail. Does that make sense? So we're just going back and forth, back and forth. Evaluate, improve, evaluate, improve, evaluate. Questions?
So it's impossible to have like two adversarial states where like the value of one is like one minus the value of the other. Because in that case, I feel like there would be like a stable equilibrium, but that stable equilibrium wouldn't maximize either of the values of the states.
So you're saying if you had two states and the values were 1 minus, so the value of this is 0 and the value of this is 1, and you're somehow seeing them kind of ping pong back and forth or something. Yeah. Now, there is an issue that can occur if you take it over. So if our R max, as we're computing our greedy function, we have more than one choice there. So you can imagine we have a state where it's just as good to go up as it is to go right. And so we compute a policy that says go right from that state. And then we run through this again. And then as we choose our greedy policy this time, instead of saying go right, we go up. So the policies are different, but their values are the same. And you can imagine just continuing forever in these cases where their values are equal, but the actual policies themselves are different. It's kind of a different question from what you were asking, but it does mean you have to be just a little careful there.
I'm guessing like the way that I was trying to define the states there is perhaps problematic in the sense that they're not independent. And if there's some dependence, then that would either have to enforce some sort of memory, or maybe it's more of like...
It should capture whatever this dependence is, right? If we since our values are always good, so let's give an example. Let's say we've got a policy that takes us to this. We are never going to improve to a policy that gives us any value less than 1. Okay? So we can't ping pong, because the way we're going to choose is we're going to be greedy. And if we know this value is 1, we're not going to do something that makes it less than 1. We might choose something here to increase it or here to increase it, but we're never going to decrease any. This policy is never going to have any state for which its value is less than the only. So that's what guarantees, because we never go back. It's not go back, it continues to go up and up and up. And it's exactly because we're doing this right next here. And we have to be stupid to choose an action that is worse than we have.
When you do this in real life, like I'm assuming to get to the actual optimal policy was like however many states there was like tons for like chess, for example. Like how do you choose? Because I'm assuming you wouldn't go all the way to the optimal state because I'm assuming I would take.
All right, so that's a great segue. Let's look at a picture from the book that's kind of nice. So this is policy iteration. We talk about generalized policy iteration. And as we look at all our reinforcement learning algorithms, they all can be kind of cast in this, almost all of them cast in this general framework. So here's kind of the idea. Let's say here we've got two lines, right? So this is V star, Y star. And here we've got V sub pi, and here we've got called pi equals a greedy V. Okay? So how does the general policy, so let's say not the generalized, the policy iteration we looked at so far, how does it work? We go through and we start with a policy, right? Y sub 0. And then we say that is ugly, pi sub 0. And then we find its value. That is, we head towards this line orthogonally and find its value. And then, once we found its value, we want to construct a greedy part of it. So we And then you come back again. And you can see how we converge to V star pi star. Questions on that one?
What does it say on the top? Like,
Oh, this is V equals V sub pi. So by the time we get to here, the value function we have is exactly V sub pi. What we can do instead, in the generalized case, is say, let's start somewhere else, just so that we're not on top of the same place. We can say, let us go towards V sub pi. Well, we don't have to hit it. We just have to improve V such that it's a better approximation to V sub pi. And once we have that better approximation, we can then construct a greedy version for that. Or at least partially greedy. Maybe it's only greedy on one state, or two states, or a couple states. And the rest it's not completely greedy. And so we can go back and forth without going all the way. And eventually, because we've got these two conditions, these two conceptual lines that we are bounded between, we'll still hit our plateau. That makes sense?
What's the benefit of like making it only some of it greedy, not all of it?
The benefit it can just be algorithmically convenient to say, I'm going to just pick one state and just make it greedy with respect to that, for instance. We don't have to iterate over all the states, for example. See, no?
But then you have to be careful that you don't make the mistake of thinking that it has converged then, right? Like if you're only choosing like one state to be greedy and then that maybe doesn't actually like fully improve.
That is a good point, is you have to make sure, you have to figure out what convergence is. Yes, so if you only made it greedy a little bit, then that won't be enough to tell. And similarly, if you're only partially computing the value, that won't tell either. So, yeah, so that is an interesting question of how do we actually know when we converge. Go ahead, Austin.
Could it potentially be, like with our old algorithm, we would have to go through and calculate the value of every single state each time we change our policy. So this way we save a lot of incremental work and only making like slight evaluations and then making a quick fix. And to handle the convergence problem, we could just still keep in mind all of the state values and when they were last updated. So keep like current state value and last state value for every single state. And only update those when each state is individually getting updated, but we still have the same sense of convergence in that way. And then the benefit would be the less computationally expensive increments.
Possibly, there's part of what you said in there, which is only updating when you need to. If you think of it, if you go update a single state value, then if you want to make something greedy with respect to that, you don't actually have to look at all states. Right? If you just updated one state value, you only have to update the states for which that can happen. Right? So, there is another kind of iteration we can do where we don't actually keep constructing policies along the way. And this is called value iteration. So this is the case we're going to basically use the definition of V star. Alfredo, do you remember the definition of V star? Or can we come up with it?
There's a max in there.
There is max. I like it. And I'll help you out. It's max actions. Right? Because basically this is the optimal policy. So we want the best possible action we can have. And the rest of it's going to look pretty similar to what we normally have. We've got a state, we've got an action. And if we look at our picture here with our agent and our environment, once we've got the action and the state, what comes out of our environment? And so we've got a state and an action. Out of our environment, we get
Reward in the state.
a reward and a new state, right? And that's prime and R. How do we model that? What's our function that we have?
A summation over the.
Okay, summation over S prime and R, because there's a lot of possibilities. What could be coming out?
The probability of S prime are given the state of the action.
Exactly, right? And what is it we're summing? Or here's our weight, and what's the term that gets weighted?
Reward.
So it's a reward plus and keep in mind, we were in this state, we took this action, we have all these probabilities. What's the other thing we're getting out of the environment besides our state? Sorry, we got our reward, and now we're here at S prime, right? What's that worth?
Of the value given the initial policy.
We're talking about the optimal policy.
Of the optimal.
Yeah, so the value of the optimal policy
S prime.
of S prime. And the last thing we got to do is, this is $1 tomorrow instead of $1 today. So it's worth less, so we got to get. Whoop. Okay, right, that's it. So we can just take that and say, let's just use this as an update. An iterative approach. We know when we converge that this will be true, right? And so let's just say V star, I'm going to call it K of S, or K plus 1, is going to be max over A, summation of R. This is a much nicer pen. E V star K S prime. Okay. And we keep going until we converge. So we have no policy in here, right? What should V0 be? Owen?
V0 would be just a constant reset.
Yeah, some initializing the random numbers. You probably don't want to actually, use uniformly random across the whole number. I mean, you probably zeros. Unless you have, if you have some prior knowledge, like you're playing a pinball machine and you went to the pinball parlor, you saw average scores are like 1 million. Set it to 1 million, right? And then go ahead and churn on it. And you'll get your optimal value function. State value, right? Once you get an optimal state value function, it's a simple thing to compute. Pi star, right? That'll just be some greedy P star. Does that make sense?
So, once you figure out all the optimal values, the way that you figure out the policy is just
Actually, let's look at that. So how do we do this? Let's say we've got, this is going to lead right into, we can actually start talking about Monte Carlo. We weren't supposed to get to some of it. But how do we construct this policy? We've got the V. So if we want to compute what pi star is for a given S,
just pick the max of the neighboring potential next states. The max is so the action will be the one that goes to the maximum.
okay, so since it's the action we want,
max of our actions.
and not the max, we want the argmax, right?
Okay, yeah, that's right.
Right? So argmax over all A, well, I guess it's going to be exactly this, right? Right, that's really the difference. This one is the value of it. That is, we're looking right, I'm kind of looking at these trees that are coming down with our expected value, and our V star says pick the max value of these, and our pi star says tell me which branch it is. That kind of makes sense? Okay, so same thing. All right, now, just make sure I didn't leave anything else off I wanted to talk about here. Thank you. Let's just put this on pause for a moment. Okay? Yeah, the thing you can do with dynamic programming. We, as we looked at the policy iteration, did an entire sweep of all the states in order to compute the value. Not only did we do an entire sweep of all the states, we did it multiple times, right, in order to converge. That entire sweep may be infeasible. Let's say we're playing chess, okay? There are so many states possible, it just doesn't make sense. But what you could do is marry dynamic programming with some actual play. So rather than saying, let's figure out all states, let's figure out the states we care about. Because there are probably a lot of states in chess that are legal that you do not care about. For example, can you have a chessboard with 8 queens on it for white? Is it possible, is it a valid state that one could get with your enemies? Yes. I queen all of my 8 pawns. Actually, I have 9 now. The 9 queens problem, right? Which can't be solved. But the 8 queens. Anyway, so don't even bother checking that state. You're not going to get there, right? Just like you're probably not going to get to a state where white is on the bottom and black is on the top, and you've got everything reversed. So it's the black starting part here and the white starting point here. That's never going to happen either. There's lots of states you're never going to get to. So start playing. The states you actually reach, figure out the values of those. Don't bother with the other ones. Leave them at 0, let's say. And as you play more, you're going to expand the number of states you reach, but it's going to be much less than the total possible number of states.
And is that where all the like the epsilon greedy exploration stuff comes in?
In a sense, we're going to talk all about this, yes, in the sense that you will have to try different moves as opposed to just living on this greedy policy according to the state values that you have. So yeah, there will have to be some exploration that happens.
Is it possible to like use some like initial knowledge to your advantage to like program some states that have like higher initial values? Like if you're like, oh, if I can get a check if I'm in this position, then you give that a...
You could do that. So that's how Deep Blue used to work. So this is the IBM dedicated hardware, and they had a bunch of end games in there, and also a bunch of opening moves, and a bunch of heuristics about how to analyze things. The current approach in reinforcement learning is forget all this stuff. Just spend more compute power and learn from scratch. Right? So the initial version of, let's see if I'm correct here. Yeah, the initial version of AlphaGo, I believe, had some encoding that they did of the boards to try and capture some interesting features. And the later versions, AlphaZero and so on, just said, just throw the board at and let it learn. two parts, two different kinds of learning happen. There's the reinforcement learning that's happening, that's telling you about rewards. And then there's the deep neural network that is approximating your Q function. Because of the fact we're never going to see all the states that even might show up in real games, and therefore we need an approximator. Let's say something like, this state is very similar to a state that I have seen and have a value for, and therefore I can give you some value.
So the game was going to happen, but when you're talking about playing the game and evaluate states as you go, how are you playing the game? Like, what's guiding the move choices you make?
Probably some idea of like what's legal is helpful.
Okay.
So you're not just randomly doing shit, right? You're actually doing things that are valid. And to begin with, you're pretty bad, right? We can often do this in self-play, right? So to begin with, you can just randomly pick a piece and pick it out of the move. And it's going to get us just a little bit to what we're talking about here. Eventually we'll get a reward, right? We'll get a reward of +1 if we win, -1 if we lose, half if we draw. And then that'll allow us to update at least some state with a new value. And then as we play more of that will happen. Part of reinforcement learning, really the problem is, we play a whole sequence of moves, and we got a reward way in the future. The credit assignment problem is, how do I credit this reward appropriately? Who should get credit for this if I won? You know, there might be stupid things I did in here, but I still won. There might be smart things. And that's a part of what we're ending up doing, is assigning this credit.
Like, so we've been saying that, like, your opponent is part of the environment, but how...
That is how we did tic-tac-toe to begin with.
But now, like, how do you simulate how they react to you on moves? Like, do you have two against each other? Like, two... Yeah.
It actually works much better. So we could play me, a reinforcement learning agent, learning against you, an actual human who knows how to play chess. And basically every time I play, I lose. I lose, I lose, lose. Right? And it's actually better for me to play myself because we're both pretty crappy. And so it'll kind of be about the right amount of challenge. You always want to be somewhat challenged. So basically what you would do is just run the same thing for white and then run it again. After that, white takes a move, run it again for black. Black takes a move.
I guess this is where Daniel was mentioning bringing in some sort of exploration. So it's
You
not
do have to have some exploration. Yes. And very often you'll have an exploration that starts out very wide, in the sense of your epsilon might be very large, and over time you might have a schedule where you anneal that and bring it. And if you're playing for real, once you train, you might turn epsilon all the way to 0. Just be completely. Okay, so we have this question of we have a value function. So let's say, given v star, compute or create I star. Okay? In the value iteration, that's exactly what we do. Right? Compute v star and figure out then from that I star. And let's assume all of a sudden we no longer have the model. So we're model free. This is now the switch from dynamic programming. In dynamic programming, everything we've done assumes we have the model. Now all of a sudden we're going to go into more of the real world where we don't have a model. It was like the MDP app that we ran last week, where it's like, I've got two states, I've got two actions, I have no idea what's going to happen and what takes me between or anything else. Easy or hard if we do not have the model?
I'm assuming hard.
It's hard. It's like, I've got a state here, and I've got I don't know, there's a bunch of other states, and I know all the values. This is a 3, and this is a 10, and this is a 9, this is an 8, and this is a 7. Tell me, what should I do here?
10.
Well, I don't know if I don't know what the arrows are, and I don't know what the probabilities are. I don't know. This is not useful to me. What would be useful to you?
Like, to know your options.
To know your options. What other function might be useful? Policy probability, we're trying to come up with that, right? So that's not useful. By process of elimination, we don't know any other functions that have just one letter in them towards the end of the alphabet. But not all the way at V.
Wait, what?
So what other functions do we know that are single letter functions?
Or Q?
Let's just think about it.
Or
V takes an S, right? Q takes an S and an A. So if I tell you, I don't know this, I can't tell you that. But I can tell you that if you're in this state and you go to here, you get a 96. And if you're in this state, sorry, I'm not telling you that's where you're going. What I'm going to tell you is action 1 will give you a 96, and action 2 will give you 93, and action 3 will give you 101. What should I do in this state?
take action 3.
Take action 3 because it's the best. Does that make sense? So, in order to use V, you need a model. But in order to use Q, you do not need a model. Because it tells you for every state what every action is worth. Total discounted reward. Does that make sense?
But if you're going to give us, like, are you giving us Q? Because I feel like that's almost the same as if you were giving us P.
Well, Q is almost even better, right? Because not only does it P, but it puts it all together and summarizes it and tells you exactly what the discount is.
So is that not basically similar to a model, like just a different form of the model?
Well, I'm saying given right now, because what would be useful for us to learn? This shows us, don't bother learning V star. You can learn that all you want. It won't help you come up with a good policy. This is what we want to learn. Okay, so it's our target. It is not going to be given to us. Does that make sense? So this is what we want to learn. In the absence of a model. Questions? All right, so let's look back at our NDP application. So here we go. And let's say we want to learn Q. What do we, so by the way, I changed the names of the states and the actions because I realized they were really stupid. So they're S1 and S2, and A1 and A2. Very easy to remember, it turns out. So, we're in state S1 right now. What is our best estimate for Q of S1 A1? Ding.
Probably 0. Or,
Is 0 better than 6?
no.
We have no knowledge other than the fact you did play this the other day, and you know it's not 10,000 or negative 10,000, but we don't know. Okay? Here's what we're going to try. By the way, we're going to be using the Monte Carlo method. Monte Carlo method is named after Monte Carlo, right? The Monte Carlo city, or is it a country?
City.
It's the city in Monaco. Okay, thank you. And it's famous for?
Casino.
Penguins and Madagascar.
What'd you say?
Gambling.
Yeah, gambling, and you said casino. Okay, fine. It's the same thing, yeah. So that's where James Bond would go, right? He goes to Monte Carlo, he doesn't go to Laughlin. Okay, but in any case, randomized algorithms are often called Monte Carlo algorithms. Okay? And there's a certain subset of those called Las Vegas algorithms that have slightly different, in any case, Monte Carlo algorithms. In reinforcement learning, Monte Carlo algorithms have a specific meaning we're going to be talking about. But we're going to be using some randomization. We have no idea what we want to estimate S1, A1. I am going to, and we want to estimate it with respect to a particular policy. So we're going to still do the same idea of evaluation, improvement, and so on. First, we're going to evaluate. We know how to improve once we get the evaluation. So we want to know, for a given policy, what do we do? And here's my policy. I'm going to move my cursor here, and I'm going to always click on A1. Okay? So it's the A1 in any state policy. And I click. And the discount, by the way, we're going to use is, discount rate is 1. So no discounting. And I am the luckiest guy alive. And I swear I have not changed this code since I last tested it an hour ago. And at some point quickly,
Wait, should we just drop everything?
hey! Okay, Daniel, what is your best estimate for this policy for Q of S1, A1?
I think just 138.
So tell me how you come about with that.
Because we've run one trial and the value from taking that action the very first, the first time we took it.
We started in S1, we took A1,
Yeah.
and then we followed our policy, right?
Right.
And we got a number of 138. So if we look at our backup function, or backup diagram, right, what we have been doing with DP is we've been saying we start here. In the case of the Q function, we actually have an S and an A, right? We have a state up above. And then we go ahead and take this action, we get some reward, we use the P function, and we go ahead and figure our Q's here, right? So we do this in expectation. Expectation in the sense of, right, try all of the new states and rewards, and here are the states and rewards, and then try the actions from there on. The Monte Carlo looks quite a bit different. We start with a state and an action, and then we actually use the probabilities of the environment to come up with a new state and a reward, right? Let's just say R1, S1. And then we take an action. What action do we take? Right? Pi might not be deterministic, so it might be probabilistic. So we'll go ahead and flip our coin and go and take a new action, A1, and then we go on and get an R2, right? And we keep going until we get to T, when we terminate. So this is a single episode randomly drawn from our pi and our p. Yes? Or we don't know what our P is. In fact, maybe there's no explicit P. Maybe we were actually, maybe this wasn't programmed. Maybe this is actually the response of some chipmunk or something, right? We don't know what is causing this, but we interacted with our environment. We got an episode. We can figure out what a reward is. If our discount factor is 1, it's just R1 plus R2 plus R3 all the way, which we happen to have as a number. So, we have now an estimate of 138. Is that more accurate than 0?
Yes.
Yeah, 0 was a wag, right? Wild ass case. 138 is from our distribution.
But this is you taking a bunch of A1s, so like what if you take A1s and A2s, and then at the end of the episode you had some total reward, what would you assign?
Well, so here's the deal. I want to know Q with respect to a particular policy. So if my policy were to take A1s and A2s randomly, then my policy is 50% of the time I take A1, 50% of the time I take A2. I would have been up here flipping a coin. My policy happened to be the deterministic one of always choosing A1. Not because it was a lot easier to press the same button over and over again, but just for some other reason.
But then what would you assign like
There
as
would-
common A1?
We'd do exactly the same thing.
You'd still assign it with
Yep. I would, as long as I started an S1, and I chose action A1 to begin with, and then I followed my policy, this gives me
Oh, I see, okay.
an estimate. So here's what I want you to do now.
So you'd compare, for example, two policies using the Q function by checking whether or not Q for every action is greater than or equal to Q for another policy.
That is what you do. If you want to compare two policies and see whether one is greater than or equal to the other, you check the Q values. And your estimate has some uncertainty in it, of course. In the same way there are estimates when we were looking at the original bandwidth problem.
Do you ever have memory in your policy, so you're like, oh, my last 5 actions were this one, and now I want to do this one?
Sure. You could have a very complicated policy, right? It's Tuesday, and I look up and it was raining last night, and therefore, since the last 2 times I chose A1, I'm going to choose A2 now. Yeah, your policy can be as complicated as you want.
You would have to like,
Just follow your policy.
yeah.
Just do whatever you're going to do when you're out in the environment. That is your policy. As long as you're not changing it as you're doing these estimations. All right, here's what I want you to do. I want you to run MD. I would like to come up with a better estimate for Q of S1A1. And so, what I want you to do is go to this MDP app. So if you look at, or compares the two, I would think would be easier. So this is, I think it's tilde Rhodes /RL/MDP_app. And then there's also a shared spreadsheet, tinyurl.com/Monte Carlo HMC.
This is for this policy, right?
This is for this policy. Yes, so use this policy. Everyone use this policy. Click on S1. Click on A1. And the spreadsheet is going to look like this. And I actually filled it out with 5 values that I did earlier that were not as lucky. Okay? Don't overwrite each other. So my recommendation is put your name in the column first. Run it 5 times. Put your name or your pair name, and then put your values there. Okay? Go.
Start at 15 to 20. 16 to 20.
That's it. That's fine. Or copy paste. Yeah, that's your policy. Keep going 5 times. Yeah, you were not lucky tonight.
Wow.
What are you doing?
So you should have 5 entries you put in there, okay? Because you can run 5 episodes.
So, let's go to this thing, right? So,
Oh,
this is what action 1
I think so. Isn't that what we're
come on.
Thank goodness it isn't automated. It's a lot of fun, huh?
I like the interactiveness.
All right, we got some.
Yep, so enter each of those once you finish those 5 rewards.
We didn't earn very much.
I know, we kind of suck at this. 17, 46, 14, 30.
No, that's wrong. That was a length. You have to do the total length.
Okay, why are people doing that?
I don't know.
Is this?
Adventure.
I don't understand.
Everyone got 5 in?
Because, yeah, you were never.
Wow.
I don't know.
People are
Okay,
really dumb.
so
23, 70,
if you didn't actually get 5 in and someone stomped on your number or something like that, that's the worst. Okay, you can take it out after class.
Oh, you got 145.
So we have an average of 35. It turns out my 134, which was to begin with, was very lucky. Could we calculate the variance here? Yeah, we could. I mean, we have the numbers. We could go ahead and do that, so we could get some idea of how accurate we are, how close to mean.
That's a big variance.
That does seem hard.
148. Oh, what?
I'm not sure it'll be.
Are you including? Yeah, no, that's the variance, not the. Also, it does include zeros, but there's a standard deviation. Wait, so this is.
Hey, I'm not including zeros, so better make sure.
Are you sure?
I'm not sure. I'm not including blanks. I don't know whether yours is.
I'm using the same thing that you did, except with a different format.
Okay, so this one just all right. That seems awful high, especially since that takes us all the way down to 0 on the one end. But in any case, this is the Monte Carlo method for evaluating Q given a policy. Follow the policy, and that'll give you an estimate. And do it more times, and that'll give you more estimates. And average them together, and that'll give you your best estimates. Okay? So, let's just go ahead and do this. All right? I'm going to go ahead and we say, oh wait, I want to know S1A2. That is, so let's make sure we understand exactly what this is, right? This is, I start in state S1, I take A2, and then what do I do?
Always hit A1.
Always hit A1, because remember that's our definition of the Q. One time, take the action that's specified, and then follow the policy. Go. Let us calculate that.
This is not going to be as fast as the A2.
This will be almost as fast. You just have to be careful the first time.
Yeah, there's still lots
You
slower.
hit S2 and then every time
Yeah.
S2.
Whoopsie.
Or no, A, sorry.
How can it be that?
Because I
It's like every
remember
time,
to
so like
S2
A2.
first, right?
Yeah.
And then you hit A1,
And
but
yeah, I
until,
can't just spam the buttons.
like you turn.
Because look, as soon as
Oh,
the
wait,
state has
wait,
it,
So I can carry.
smack the, yeah.
Oh my God.
There we go. See my point.
It's fast if you get one again.
All right, clearly this task is not fast enough.
Okay,
Oh,
we'll
no,
just like
no,
record
no.
that.
Yeah.
Oh, good, good, yeah.
Are we changing to restore to me?
So we are changing the same thing, that's just giving us,
Yeah, 5.
so.
Then refresh.
Okay, ready?
We have
Blah, blah. Oh.
the,
Okay, we'll just record this so we can start.
discounted, right, we got the long term one. Clearly, what we're calculating is just going forward. And taking this action.
But aren't you, I mean, like, anything like if you're initially in the state, when you start.
You start in that state, take that action.
And then whatever happens.
Whatever happens, happens.
Okay, let's just look at the initial, so like we started in S2, and then
That's fine.
But if we started.
If we start in S2. We'll go ahead and talk about S2 in just a second. So that'd be a good. Can we get additional information from our episode? Would be interesting. Okay, what do we got? All right, let's say that that's accurate. Although I'm guessing we have fewer samples than we did before. If we're in S1, are we better off, from the information we have so far, taking action A1 or A2? A1, because our Q tells us so. All right. If we look at the optimal action, is it necessarily to take A1? How could it not be?
Our data's off.
Okay, that's one possibility. Our data's off. We got random numbers that were different. Okay. Let's say that these were the actual Q values for this policy. Is it possible that this is not the optimal action taken in this state?
We got a better policy.
Yeah, there could be a better policy that eventually we'll get to as we do more and more iteration, right? As we take this new policy, we make it a different value, and then that may lead us to a new policy and so on. So this may not be our final action, it just happens to currently be our best action that is in front of us. Two things I want to talk about. One, if I look back at this episode, let me start another episode and hope it's quicker. Okay. Let us look at episode 2. Is there any additional Q information that I can get besides S1A1? I started in S1A1. I went through S1A1 a lot of times. I did go to S2 for a short period of time. The question is, is there any additional Q information I can get from this?
Well, we can see that there's no reward for that state. We're moving into state 2 action 1.
So when I was in state S1 and I took A1, I went to S2 with 0 reward. So that's true. I did get an immediate 0 reward. But is there anything I can get as far as the Q value gives us a lot more than immediate reward, right? It gives us our total over time.
Right, well, making that transition might change like which branch we're on or which possibilities we're going to try.
It could. That's true. What state are we in here?
S2.
And the action we're taking?
A1.
So we're in state S2, we take action A1, and we get a certain set of reward here. Right? Not as much as the entire episode, but we get from here down. Is that an estimate of the reward you get from being in state S2, taking action A1? Yep, that is an estimate. So we find our first S2A1, and we say, take that, and everything down, and come up with a board. Okay.
But that only works if like it's not dependent on the previous students.
So let's think about this. You're saying that it's only work if the environment does not depend on the previous history of what has happened, but is totally contained within the state itself. Name that property. Or ask a friend.
It's a Mark.
That's the Markov property. What's our assumption about our environment? That it's Markov.
So does that mean like if you have an S1 like very close to the end, that you can also take like a sum down of that S1, and that's also an estimate?
So I want to make a distinction and postpone it for a moment between first visit and every visit. We are looking for the time being at this case. The first time we hit S1A1, we're going to use from that on down, and that's our estimate. There is another option which is every time you hit S1A1, you've got a new estimate. And so we would have a lot of different estimates that we would get from this particular episode. But I'm going to ignore that for now and just look at first. Okay? So for the first, we look at the very topmost S1A1, sum everything below it, and that gives our rewards. And then we can also say S2A1. Doesn't matter how we got here because of the markup property, we can go ahead and use it.
But that sounds a little strange. Like, is every visit like also a viable method to use?
So remember I said we're going to postpone it? We're going to postpone it.
Okay.
So I refuse to answer.
Okay.
Okay.
I was gonna ask, are these policies like normally random, or do you make them such that it explores in a way that you want, or?
Why do you ask? It's a good question. Why?
Because I feel like in this example it's helpful because you're always doing the same action, so you're learning things about taking that action, where if you just did it like randomly, it wouldn't be as clear about what's happening.
So let's come back to this. We want to estimate Q prime. We know what Q prime. Q, so pi. We have pi. So given pi, estimate Q pi. We got an estimate for S1A1, right? Whatever it was. We got an estimate for S1A2. How did we do that?
Did just only that.
We took that action to begin with and then continued our policy. We also have an estimate for S2A1. How did we get that? We didn't actually calculate it yet, but we do have that on our trace on our episode. So we go find the S2A1, do some simple arithmetic to figure out this all the way down, and we come up with an estimate. There's an S2A1 over here too, do the same thing, do it for all of our traces that happen to have an S2A1. Yes?
So sometimes with training models, you run into the problem of like unbalanced data sets. And if we only like get our S2A1 estimates by looking within traces of our other trials, would we run into that problem of having our S1A1 estimate be way more accurate than the others?
Well, the S1A1 will be more accurate in the sense that we might have no S2A1s in a lot of our episodes. But if we have an S2A1 in there, it should be fine.
So for the DP method, we had a strong sense of like convergence. How do you know if you're converging at all in here?
The law of large numbers.
Okay.
You know,
Try it enough.
So similar to what we looked at, let's say the bandit problem. How do you know? You could be looking at confidence bands and things like that. What are we missing here?
S2A2.
S2A2. Are we ever going to see it in these traces doing what we're doing? Well, we know we won't because we know we start in Q1. I mean, I can tell you that it always starts in Q1. And we never choose action 2. So we're never going to get an S2A2. So, one solution unvisited state action pairs. Exploring starts. That's actually what we did for S1A2. We said, you know what, when you start out, go ahead and pick one of the actions that you wouldn't normally choose based on your policy. Choose it, and then stay with your policy. Could we choose S2, A2? But we have to figure out how to get to S2. Right? You might say, I don't know, what happened if I put a question mark S2 in the URL? Wait, that's supposed to work. What if I put a capital S in there? Hey, but you start in S2. Okay. So it depends on your environment whether you're able to try these exploring states or not. If you've got a self-driving car out on the road, you probably don't want to say, what happens in the state where I'm going 50 miles an hour 2 feet from a pedestrian? Right? Let's see. First, it's hard to do. It's hard to get volunteer pedestrian. So that can be difficult. And that's why we may need to try some epsilon approaches as a way to explore our state action space. Does this make sense? Let's look at every visit count and first visit. We've got just a second. And the question is, what's the real time? 2:26, 4 minutes we can do this. So here is our environment. We've got a state and a terminal state. And we get a reward of 1. We have 50% probability. And a reward of 0 with 50% probability. We just have single action. The action either stays in the state, gets a reward, or goes to the terminal state. So if we look, we should be getting half the time, we should get a total reward of 0, right? Half the time, we just go to our terminal, we're done. A quarter of the time, we should get a total reward of 1, right? We choose this, and we're done. Half the time, or 1/8 of the time, we should get a 2, and so on. If we use the first visit, we'd expect an 1/8 of the time, we're going to get a 2 reward. Right? What does a 2 reward look like? A 2 reward looks like SA, we start in our state and go in our action, we get a 1. Right, that's what the episode looks like. We get a reward of 1, we get a reward of 1, and then we go to the terminal state. This is a true estimate of the expected reward. Because we're going to exactly half the time choose ones that give us 0, and a quarter of the time choose ones that give us 1, and each time we choose ones that give us 2.
So why is it a quarter?
Because the way you get a 1 is first, you take this one with 50% probability, and then you take this one with 50% probability. So that's exactly. If we do every visit, we would put 3 numbers into our estimate for Q of our single state and our single action. So in the case of first visit, our S comma A is going to equal 2, right? Because we have a reward of 2. In our every visit, S comma A, we have an estimate of 2, because we were in S and A, and we got a reward of 2. And then we're going to say, oh, the next time we were in S and A was here. How much reward do we get from here on out? 1. Oh, and we were in S and A here too, and the next time was 0. In fact, every single episode is going to have a 0 in it. This should be contributing an estimate of 2. But we're actually got an estimate, basically a 1 here. So it is biased. First visit has nice theoretical properties, such that it always converges. Every visit will converge. There are still some open questions about every visit. In practice, so this is what people use. Because it's easier, because we want to be looking at each step along the way anyway for other states and actions. And it's easier to just look at every state in action and just throw them in blindly, rather than have to keep track, have I seen this one before or not? Okay. Does that make sense or not? So in practice, people use every visit. It doesn't have quite the theoretical guarantees that first visit does.
Okay. Just to clarify, when you say every visit, you mean that you treat, like within an episode, you construct like a bunch of mini episodes just based off like what's
All of the suffixes
Gotcha.
of the
All the
episode
suffixes.
become new fodder for our in here.
Why is it, I still don't see why it should be theoretically biased, like, because it should be,
But let me give you an example. An eighth of the time, we should be getting a 2 as our estimate. An eighth of the time, we're actually going to get an estimate of 2, 1, and 0. So 1 is what we're going to be feeding in.
I guess what he's saying is that like it's equally likely that it would be estimated higher, like for a different episode.
Our episodes always look like this. We have a bunch of 1s and then a 0. And so however many 1s there are, right, if we should have been saying an estimate is 5, we're now going to say we're going to put in a 5 and a 4 and a 3 and a 2 and a 1 and a 0. Right? Every time we're going to put in a 0. So we're going to be over biasing the 0. 0 should be happening half the time.
I see.
And it's actually happening, we're actually introducing it every single time.
is it the same a third of the time you get a 1, and a third of the time you get a 2?
Yes, it is. But if we look at taking our average over time, we are going to have more zeros. Let's just even look at the 0 case. We're going to have more zeros than we should, which will bring it down. Because we should only have half of them be zeros. And we will have more than half be zeros, because we've got extras for every one of these. Okay. Okay, I'm sorry I've gone over. Have a good weekend. See you on Monday. I said on Monday that the programming assignment was due on Wednesday of next week. It's not. It's due Tuesday of next week at 11 p.m. So it's in the schedule. It was always in the schedule that way. I just want. I will be in the cafe after this. And a reminder, office hours next Tuesday, 1 to 4 in the afternoon.